is process of light emission, and dosimetry is a dose measurement of ionizing radiation. Luminescent dosimetry is then a dose measurement relating with emission of light from a material.
There are two types of luminescent dosimeter, which are thermoluminescence dosimeter (TLD) and the optical stimulated luminescence dosimeter (OSLD). There are 5 steps of how the TLD works. Step 1. The ionized radiation passes through the detector and the chip inside absorbs the radiation. Step 2. As the crystal is a material containing impurities inside, it traps the electrons in the band gap and holds them there. Step 3. The trapped electron represents stored energy. Step 4. The crystal is then heated, where the trapped electrons return to the ground state and emits photons of visible light. The light emitted is counted by a photomultiplier tube. The amount of light emitted relative to the temperature is known as the glow curve, and from the curve we can determine the dose. And finally, step 5. After the measurement is taken, the TLD is annealed at a high temperature as to zeros the TL material by releasing all the trapped electrons, and then the TLD is ready to reuse. Same as TLD, it has 5 steps on how it works but slightly different. Step 1. The ionized radiation passes through the detector and the crystal inside absorbs the radiation. Step 2. As the crystal is a material containing impurities inside, it traps the electrons in the band gap and holds them there. Step 3. The trapped electron represents stored energy. Step 4. The crystal phosphor is being exposed to light, where the trapped electrons return to the ground state and emits photons of visible light. The light emitted is counted by a photomultiplier tube. And finally, step 5. After the measurement is taken, the OSL is annealed at a high temperature as to zeros the OSL material by releasing all the trapped electrons, and then the OSL is ready to reuse.
This figure shows response of OXL detectors in aperture units versus accumulated dose in centigrade for cobalt-60 irradiations. 3 different detectors were used at each dose value. For each detector, the response is the average value of 3 readings. The solid line shows a linear fit through all of the data points with an intercept at 0 dose of negative 6.6 plus minus 6.0. This figure shows the curves of TLD exposed to 6 mega electron volt beam at different dose range, which is for A 0 to 8 gray, for B 0 to 10 gray, and for C 0 to 30 gray. The solid line represents the linear fit and the dot line represents the quadratic fit. This figure shows dose rate independence by the independence from Faraday cup signal, which is at the bottom abscissa. The shown uncertainty is the standard deviation of the 4 repeated measurements of each point. The linear fit of all points is given by the dashed line function and results in reduced x squared equals to 0.95 and A equals to negative 5 plus minus 27 to the power of negative 5 gray per volume squared. This figure shows dose rate dependence of OSL. The linear fit, which is the solid line, results to reduced x squared equals to 0.63 and A equals to 17 plus minus 18 to the power of negative 5 gray per volume squared. In conclusion, there is no dose rate dependence for both OSL and TLD. These figures shows area and personal dosimeters, which are OSL, TLD100H, and TLD100 curves versus photon energy. For TLD100, both curves showed significant overresponse curves. For OSL and TLD100H, the curves are slightly overresponse. It can be concluded that OSL dosimeter yields a better energy response performance compared to TLD100H and TLD100.
For advantages, generally due to their small size, TLDs are convenient for dose distribution measurements in medicine and biology. Lithium fluoride, magnesium titanium, which also known as TLD100, having a nearly tissue equivalent material of good sensitivity, it is perhaps the best choice for radiation dosimetry. It has been commonly used for medical purpose, as it has an effective atomic number of 8.2 compared to 7.4 for tissue. Luminiscence dosimetry also possesses of high sensitivity that allowing doses as low as 1 mg to be measured. It has linear response with dose up to at least 1 gray and good energy response after X-ray irradiation. It also able to be reused and have resistance to high humidity and to high magnetic fields. For disadvantages, TLDs are relative dosimeters, so they have to be calibrated against absolute dosimetry system, such as a calibrated ion chamber or a cobalt-60 gamma source. The use of TLDs in electron beam dosimetry is more complicated than its use in photon dosimetry, because for each incident electron beam energy, it will obtain a different dose response. As mentioned earlier, TLDs have linear response with dose up to at least 1 gray, but the response is not linear for large doses, and its efficiency depends on the radiation field. Particularly with respect to high sensitivity, it is the decrease in the response of TLDs with increasing ionization density of the radiation field, which may lead to the underestimation of dose after heavy charged particle irradiation. In the past, the TLD system need manual handling, annealing, and readout, but in modern TLD system, all of these are fully automatic. There are three main usages of luminescence dosimetry in clinical, which are the postal dosimetric service, in-phantom measurements, and 2D thermoluminescence dosimetry. The most frequent routine applications of TLDs in radiotherapy are meal dosimetric service of radiotherapy units, such as those organized by the IAEA. The lithium fluoride TLDs are irradiated under specific conditions in a simplified water phantom at the participating radiotherapy center and returned to the IAEA dosimetry lab for evaluation. Several corrections for dose dependence, energy dependence for MV X-ray, and fading are applied to increase accuracy. The accuracy of the measurement can be better at 1%, but the overall extended uncertainty of the method, including the calibration, is about the level of 2%. For in-phantom measurements, small-sized luminescence detectors are used for point light dosimetry in dosimetric phantoms. TLDs in clinical environment are almost used for research purpose only, because in routine clinical work, manual installation and readout of large numbers of detectors need lab and it is time-consuming. For photon beams, the mini phantom is placed on a platform which is located at 100 cm from the source, with the mini phantom located on top of the platform in the center of a 10 cm x 10 cm field. For electron beam, the top of the phantom is set at 100 cm from the source. Any difference between this irradiation geometry and the Linac calibration geometry are accounted with appropriate geometric and TMR corrections. In modern radiotherapy, two-dimensional or 2D dosimetry with high spatial resolution is required for modalities where steep gradients of dose distribution occur, such as in the case in scan beams of protons or carbon science, or even in various modalities using photon, MV X-ray, medical accelerator beams. This figure shows a 2D TLD system developed at Institute of Nuclear Physics, PAN. It consists of TL detectors in the shape of a voice, a dedicated TL reader equipped with suitable heating system and a CCD camera, and dedicated software for image acquire and post-processing. There are few advantages of the developed 2D TLD system, which including direct digital output of dosimetry data from a pre-calibrated 2D detector, which shows linearity over the dose range from 10 mg to 10 Gray. The data output is in ISCII matrix format and dicon adaptable. It has good spatial resolution, able to reuse, have good mechanical properties in which its flexibility and water resistance. This 2D TLD system was applied for 2D dosimetry of 6 MV radiotherapy beams, brachytherapy source, 6 and EV proton beams, and so on. The convenience of use and the short time required to evaluate 2D TLD voice make them very suitable for QA in radiotherapy, for example in verification of treatment plans.